16.1 through 3 covers planar rigid body motion, both translation and rotation. The objective that you're going to be learning today is how to categorize motion into translation, rotation, and general plane motion. You'll then be able to use these to calculate the position, velocity, and acceleration of points. And then we won't actually get to, but you will have the ability to calculate the speed of gears and of pulleys. So why do we need to be able to do this? Well, what we've been looking at is just a particle, and it's going along a path, and it has some velocity. We even looked at a collection of particles. However, real life, we have solid objects that have many different points on them, an infinite number of points, you could say, and they can both translate and rotate. And so that's what this is going to cover, is how to analyze those systems. So, rigid body motion. What is rigid body motion? Well, essentially, what you can do is you can have an object and it moves to the side, and it can rotate. Again, before we just had a particle and it moved to the side, but we didn't care if it rotated and we couldn't tell if it rotated. However, now since we have something that is kind of a peanut shape, now we can tell if it rotates, and there's going to be multiple points on that, and they're going to behave differently depending upon how it actually rotates. So, what is planar motion? That was in the title for today. Well, you can think about it as there is a sheet of paper, and you have an object on that sheet of paper, and that object can move, it can rotate, it can go through kind of any path it wants to. However, what it cannot do is it cannot leave that sheet of paper. If it leaves the sheet of paper, it is no longer planar motion. So we're talking about everything that is on kind of a flat surface, which is nice because that is how I am drawing things. So there are different types of rigid motion. The first thing we're going to be looking at is just has the points moving directly in one direction. So they could be to the right, they could be up, they could even be at an angle, but they cannot go along a curved path. And this is called rectilinear translation. I should also define translation. If something undergoes translation, then every line segment on the body remains parallel to its original direction during motion. So this is essentially saying there is no rotation. So it can move at an angle, but if a point was directly above a point when it started, it still has to be right above that point. It can't rotate whatsoever. The next type of translation that we're looking at is called curvilinear translation. And so now it doesn't have to go in a straight line, it can go in a curved path. However, since it's still translation, a vertical point still has to be vertical in the final location. If you don't want a vertical, if you don't want things to remain the same, then you have to undergo some rotation. There's a couple ways you can look at it. You can either, it's rotating about a fixed axis. So you can think about taking an object and running a skewer through it and then spinning it along your skewer. And so what you're going to see is that a point goes from one side to another. And so this is rotation about a fixed axis, and I'm going to show it differently here in just a minute as well, so you can see both ways that this can happen. Because I've drawn more of a kind of a three-dimensional motion here. And then the final one, the final type of motion, is going to be called just general plane motion. And so this is the one that allows rotation in a planar motion. So here you see the peanut is going from left to right, and it goes a curved path, so it's curvilinear, but it's not translation because the point that used to be vertical, so the blue point used to be right above the green point, it's no longer right above the green point. So it's no longer translation, and so we just call it general plane motion. So let's first talk just about translation. So here is our peanut-shaped object, and here it is at a later time. And so we have point A in both locations, And so we can say the vector that goes from the previous location to the new location is r sub a. And we're going to do the same thing for point B, except for what we've done here is we have the origin located at point A, so that's really why RA goes from A to A. But what we're really doing is going from the origin to the new location. So this is going to be RB. And if you remember back, we have RB with respect to A, which is B's location with respect to A. So if you're at A, how do you get to B? And so if we want to write out RB, you can write it out as RA plus RB with respect to A. So again, you can either just go from the origin to RB, or you can go from the origin, from the origin to B, or you can go from the origin to A, and then from A to B. So it just depends upon what you want to do. Now, that's great for the location, but what's the velocity of B? Can we determine that if we just know something about A? Well, what we have to do is we have to take the derivative, so we have the velocity of A, and then the derivative of B with respect to A. But if you look at RB with respect to A in the original coordinate system, so the x and y coordinate system that we use for the left, and you look at it in your new coordinate system, which I've now drawn as x prime, y prime, it's going to be the exact same. It's still going to be, let's say, 5 units straight up. And so that doesn't change as long as you're undergoing translation. It'll change if you do rotation, but not if you do translation. So that just means that this term goes to 0. So the velocity of point B is equal to the velocity of point A as long as you're only undergoing translation. You can do the similar thing to figure out the acceleration of B, and it's just the acceleration of A, because again, the second derivative of r, B with respect to A, is also going to be 0. So all points have the same velocity and acceleration if the rigid body is just undergoing translation. So if it's undergoing some other motion that involves rotation, then this is not true. But as long as it's a rigid body and it's undergoing just translation, then all points have the same velocity and acceleration. Next, we're going to look at rotation about a fixed axis. So here I'm going to go back to planar motion, so I'm not going to go to an object and skewer it. I'm just going to have a piece of paper, and I'm going to have an object on it, and now I'm going to skewer through the paper, you could think of. So I'm going to skewer there at the white dot, and so I can rotate my peanut shape about that white dot. And so if I have a point on the red peanut, it is then rotating to the second location and it is there as well. And since we're rotating about the fixed axis, if we draw a line from from the point that is rotating, which I'll call the origin, to the point on the red peanut, and then do the same thing on the orange peanut, those are going to have the same lengths, because it's not going to stretch because it's a rigid body. And so if we kept going around, we'd end up with a circle, because we'd always have the same radius, which is just the distance from the point of rotation to the point that we're looking at. You could also look at the angle that it rotates, which I'm labeling here as theta. And so a lot of times that's what you want to know. And so the angular displacement is theta. You often want to know the angular velocity as well. Well, that's just the displacement with respect to time. So how long did it take you to displace that many degrees, or radians as we're really going to be using? And that's just going to be omega, angular velocity. And that's going to be in radians per second. We're also going to be calling counterclockwise positive, so I'm going to try and be consistent with that. There's nothing special about counterclockwise being positive, but it just helps our conversations if we can be consistent. Next, we're going to look at angular acceleration. So now we're just going to take the derivative of angular velocity, and we're going to end up with the second derivative of theta. So it's just alpha is what we're going to call it. And this is just the angular acceleration, and it's measured in radians per second squared. And again, we're going to call counterclockwise a positive. Just like there was what I've been calling the other equation for acceleration and position and velocity that does not involve time, there's the same thing for rotation about a fixed axis. So we have alpha is equal to omega d theta, and this was also written as alpha d theta is equal to omega d omega, and remember the equation before was acceleration ds is equal to velocity dv. So that's the parallel equation here. And so again, you can use this even if you don't know anything about how things vary over time, as long as you know how the acceleration varies with position and and you know something about the velocity, then you can use this equation. Again, going back to the kind of the rectilinear, the things that you're more familiar with, if we had a constant acceleration, then we had a set of equations that we could come up with that were pretty easy to use to find the position and the velocity. So the same thing here, so we can do the velocity, angular velocity, is equal to the initial angular velocity, omega naught, plus the constant acceleration times time, and then we have theta is equal to theta naught plus omega naught. Oh, that should be omega naught t. Sorry, I don't think I can go back in and add that right now, but it should be omega naught t plus 1/2 alpha c t squared. Let me see. There, that should be a t, omega naught t. And then we have the kind of the other equation here too, where if you know your initial conditions for your position and your velocity, then you can solve for your new velocity at a later time if you know the later position as well. So let's say you want to know the velocity of a point in general though. So here we have v is equal to omega r, where r is just your vector or your distance from your origin. And this is just an equation that you have to remember. You can write it in vector form, so you can do velocity is equal to omega cross r, and I'll show you here in a minute that this ends up being what you're looking for. You can think about it as if you go around your circle, what you've done is you've gone 2 pi radians, and so if you've done that in a certain amount of time, then you can go from velocity to velocity of your point here as well. But in general, just remember the equation. The velocity is equal to omega r, so the farther away that you are, so if your r is very large, then your velocity is going to be very fast. Also, if your angular velocity is large, then your velocity is going to be very fast as well. So the terms make sense. And you can also rewrite this as r theta dot and then u hat theta. Remember, u hat theta is the unit vector that is in the direction of your changing theta. So it's the same thing as we have on the left, where we have velocity is equal to omega r, except for now we have omega, we have theta dot, and for r just is still r, but now we know the direction of the velocity, whereas before we didn't. Next, we're going to look at the acceleration of a point. So there's going to be 2 components to this. You can look at it in normal and tangential coordinates like we looked at before. And so before we had the acceleration was equal to the normal. Oh, this should just be an. This is incorrect as well. This should just be a. This should just be a in general. And so it's going to have a normal component and it's going to have a tangential component. And so we know the tangential component is just going to be alpha r. So it's just the derivative of the velocity from above. However, there's going to be a normal acceleration as well. So there's going to be acceleration that points towards the origin, towards the point that it's locating about. And that's going to be omega squared r. So if you remember back to the normal acceleration from before, it was v squared over rho, where rho was our radius of curvature. But now, since our radius of curvature isn't changing because we're confined to going in that circle, so rho is equal to r. So now if you write a sub n is equal to v squared over r and use our equation from up above, where v is equal to omega r, you can write omega r squared over r, and so that's just omega squared r squared over r, and so you end up with omega squared r. So you can see that they do give you the same thing, so that does check out. So remember, this is not alpha, but this is just the acceleration of the point in general. And if you want to do it in vector form, which is always nice as well, you can also write it in this way. Wow, I apologize for all the mistakes in this video. This should be an r. So this would be the direction from your origin to your point. And so what this is just saying is that the acceleration is actually going towards your origin, not away from your origin, and that's why we have the negative sign there. And so this is just another way of writing the exact same thing.